Hi everyone, my name is Shuai. Today, I'd like to share you about some work that we did in apply reliable virtualized NVMe storage systems in public cloud infrastructure, aka Spool. This is a joint work with my colleagues from Shanghai Jiao University and Alibaba Cloud. The first part is introduction and motivation. The performance of an I/O device is impacted by both the storage hardware and software. Emerging NVMe SSD devices based on the latest VNAND technology have increased the LPS to 1.0 million and reduced the latency to 10 microseconds. Software has become the performance bottleneck. The big three of cloud computing, Amazon, Azure, and Alibaba, are providing the next generation of storage optimized instance for workloads that require high I/O throughput and low latency. These products are driven by local devices that eliminate the long latency over the network, while parallel researchers focus on improving the read-write throughput and reducing the latency of virtualized NVMe devices. They acknowledge the reliability problem. High reliability is the most important and challenging problem for cloud provider. Firstly, the NVMe virtualization systems need to be restarted often to resume from software failures or upgrade. Secondly, local NVMe devices failure occur frequently due to higher storage density and vulnerable components. Finally, the NVMe virtualization systems need to be upgraded often to add new features or apply new security patches. There are generally three I/O virtualization mechanics: Virtual, PCIe pass-through, and SPDK. Spool is proposed based on the SPDK NVMe driver, but focus on the reliability of the virtualized storage system. However, the current failure recovery method with SPDK results in significant unnecessary data loss. For Azure, a device failure results in the entire machine being taken offline for repair. For SPDK, the administrator could directly replace the failed device through hot plug. Our in-production shows that only 6% of the hardware failures are due to real media error, and most of the hardware failures can be resolved by simply resetting the NVMe controller. On the other hand, previous work results in poor availability. VM migration is too costly for an instance with local storage device to upgrade the virtualized storage system. It is not supported by cloud providers. The downtime for SPDK restart to upgrade is up to 1,200 milliseconds for Samsung PM963 and more than 2,500 milliseconds for Intel P3600. The long downtime hurts the availability of the I/O virtualization systems. The second part is design of Spool. Spool is comprised of a cross-process journal, which records each I/O request and its status to ensure data consistency. A fast restart component, which records the runtime data structures of the current Spool process to reduce the downtime, and a failure recovery component, which diagnoses device failure type online to minimize unnecessary disk replacement. Based on the three components, Spool ensures the high reliability and the availability of the storage pool. In addition, by adopting the SPDK user space port driver specification, Spool eliminates the overhead of system calls and data copies between kernel space and user space on the host and achieve high I/O performance. The third part his Spool key ideas. The Virtual protocol is adopted by Spool, and the I/O requests are processed in producer-consumer model. In the first step, the guest driver places the index of the head of the descriptor chain into the next ring entry of the available ring, and the available index of the available ring is increased. Then, the driver notifies the backend that there is a pending I/O request. In the second step, the backend running in the host obtains several head indexes of the pending I/O request in the available ring, and increases the last available index and submits the I/O request to hardware driver. Finally, once the request is completed, the backend places the head index of the completed request into the used ring and notifies the guest. In general, the storage virtualization systems runs well with the above procedure. However, in the case that the backend obtains two I/O requests, I/O1 and I/O2, then the last available index is increased from I/O1 to I/O3 in the available ring. If the storage virtualization system restarts at this moment, the last available index will lost, which means that it does not know where to persist the I/O request after the restart. Even if the last available index persists, there is no way to know whether the obtained I/O1 and I/O2 have been completed. It will simply continue to process the next request based on the last available index. The previous obtained incomplete request will be lost. Therefore, Spool persists last available index, the head index, and the status of each request. The request is given one of the three status: in-flight, done, or none. An intuitive idea is to use shared memory as a journal to save this information with low latency overhead. However, it is challenging to ensure the consistency of the journal itself. The process of each I/O request in Spool involves updating the last available index and marking the state of the request as in-flight. During the processing, if Spool restarts or the controller is reset, the request is lost. So, we need to guarantee the instructions to increase last available index and change the request status are executed in an atomic manner. We design a multi-instruction transaction model to solve this problem. In T0, we make a copy of the variables to be modified. In Ty, the transaction will be in the start state. After all the variables modified completely, the transaction will be in the finished state in T2. If any failure occurs in one transaction, we roll back the transaction to erase all data modification with a copy we made in T0. Besides, we design an auxiliary data structure carefully to eliminate the overhead of making a copy in T0 using a union type. The status, last available index, and the head index of the related request are packed into 64 bytes and a union memory block with a 64-byte value. We could update these three records within one assignment instruction. Algorithm Y is for cross-process journal. In step 1, Spool pulls a head index from the available ring. In step 2 to 4, it stores transaction state, last available index, and the head index to a temporary variable. And in step 5, Spool processes these three records with the assignment instruction. In step 6, Spool processes the status of I/O request. It is worth noting that the journal is unmapped to a shared memory. In step 12, after put a head index into the used ring, the step may go to step 10 or 13. For batch compilations, every step Spool takes in algorithm Y is likely to restart for upgrade. So, in recovery scenario, the new Spool process checks the last transaction state and decides whether to redo it. Then, the status of IO request is repaired based on the used index of array and the last available and the last used index in journal. Next, I'd like to talk about optimizing Spool restart. There are two stages for a restart: init EO and probe devices. Our experiment shows that the whole time spent on obtaining the memory layout information of heap pages is 800 milliseconds, accounting for 70% of the total downtime for Samsung PM963 NVMe device. A long EL initialization results in a long start time and poor user experiments, because the operating system will never change their physical location, so that the runtime configurations and memory layout information can be reused. When probing the NVMe devices during the restart of the SPDK driver, more than 90% of the time is spent in resetting the controller and the NVMe devices. The data structures of the NVMe device controller are not broken after a restart, so the controller information can also be reused. The key idea here is to reuse the related information of previous Spool process. After the first startup of Spool, we store the related information, including global runtime configurations, memory layout information, and NVMe device controller related information in the memory mapped fields that reside in the memory. If Spool starts, it directly obtains the required information from the memory mapped fields with short latency and operates normally. The challenging part here is that the context of the IO request has disappeared with the exit of the Spool. Therefore, we need to ensure the admin queen and IO queen of the device are completely clean. So we catch the termination signals, include sigterm and sigint, to ensure the completion of all in-flight IO requests before actually terminating. Regarding the sigq signal, which could not handled by process or abnormal exist, we reset the controller to restart as 0. The last part of our work is hardware fault diagnosis and processing. Generally, if a device fails or is hot removed, it will trigger SIGBUS error that causes the host process to crash. If guest VMs still send IO request to the field device of the host to improve reliability, a SIGBUS handler is registered into Spool. Spool identifies the failure type by the smart diagnose. Once a hardware median error is verified, Spool proactively fills the submitted IO request and return IO errors. After that, all the subsequent IO requests to the field device will return errors to the guest VM directly, until a new device is hot flushed. Meanwhile, the smart diagnose will set a report for DVOPS. The hot flush features in the driver of SPDK is utilized in Spool. Hence, the field device can be replaced directly. For the other hardware errors, such as a data link layer failure. Diagnose informs Spool to reset the controller. During the reset process, the I/O request from the guest VM hung. After the device is fixed, the in-flight requests in the journal are resubmitted automatically. The last part is evaluation. Table Y summarizes the hardware and software specification of the experimental platform. Table 2 lists the generated FIO test cases. Firstly, we design an experiment to evaluate Spool reliability of handling hardware failure. We expect Spool should not affect the I/O operations on other devices of the same node, and the VMs that are using the field device should receive I/O errors instead of the existing anomaly. We launched 2 VMs on a hardware node equipped with 2 NVMe devices. The storage service for VM2 is offline when SSD 2 is hot removed, and then it is back online automatically when the device is hot flashed. The storage service for VM1 is always not affected. To validate the reliability of Spool in handling upgrades without resulting in data loss, we designed an experiment that restarts purposely, stops and restarts, and randomly kills and starts. In this experiment, we rely on the data verification function in FIO to check the data consistency on guest VM. FIO runs completely with no errors. In other words, Spool can guarantee data consistency during upgrades. Figure 14 shows the restart time breakdown of SPDK and Spool. As we can observe from this figure, Spool significantly reduced the total restart time from 1200 milliseconds to 115 milliseconds on Samsung PM963 SSD. This significant restart time reduction originates from the reduction of EL initialization time and the NVMe probe time. We also report the I/O performance of Spool compared with native Virtual SPDK vhost block and SPDK vhost SCSI. There are 2 cases. An NVMe device is only allocated to a single VM, and an NVMe device is shared by multiple VMs. Figure 15 shows the IOPS and the data access latency to an SSD. Spool achieves similar performance to SPDK. Figure 16 shows the IOPS and the data access latency when 3 VM shares an NVMe device, and each result is the sum of those of all VMs. Spool improves the IOPS of random rate by 60 compared with SPDK vhost block, and Spool reduces the average data access latency of random rate by 54% compared with SPDK vhost block. To measure the overhead of the cross-process journal, we implement a Spool variation, Spool node J, that disables the cross-process journal. Figure 17 shows the data access latency and the IOPS of the SSD with Spool and Spool node J. Spool increases the average data access latency no more than 3% and reduces the IOPS by less than 1%. Figure 18 shows maximum performance of a largest specification instance compared with Amazon and Azure. The maximum IOPS of a single disk is 50% higher than that of competitive products, and the maximum IOPS of the largest specification instance is 51% higher than that of the competitive products. That's all about our work. Thank you for your listening. Any questions are welcomed.